The next question concerns the Doppler shift, and this is one of the rare occasions where I'm going to say introductory problem sets show you how to reason out the Doppler shift, but I'm okay with it if you just use the equation. So let me quote the equation, and I think I've got the subscripts right. Previously I was using it, I had two different subscripts for the source, and one of them was a subscript that should have applied to the detector. Alleviating that confusion, the situation we have is we have a source that is emitting waves and a detector over here that picks them up. That's supposed to be a Doberman Pinscher's ear with fur on the edges. Okay. Now, if the detector is moving toward the source, then we're going to say that the velocity of the detector, which is v sub d, is positive. If the detector is moving away from the source, then that's going to be negative. Now, different authors will use different conventions here. I believe your book's convention is that if the velocity of the source is in the same direction as the velocity of the detector, then it has the same sign. Okay, so in this case, if the velocity of the source is this way, then it has the same sign as the detector would if its velocity was in this direction. This case, this is going to be a positive source velocity. So the negative source velocity would be approaching the detector. The positive detector velocity is approaching the source. So with that convention, we're going to use c for the velocity of the wave. So the wave velocity is c, and the frequency observed by the detector is equal to c plus velocity of the detector over c plus the velocity of the source multiplied by the frequency of the source. Now, why does that make sense? Okay, well, first of all, if the source is stationary, then velocity of the source is 0. If the source is stationary and the velocity of the detector is positive, then the detector is going to encounter these waves more quickly than it would if it was stationary. Okay, well, if it was stationary, it would be detecting the waves at the frequency at which they're produced. So that the frequency observed by the detector, which is approaching a stationary source, will be higher than the frequency of the source. And that is taken care of here. We have c plus velocity of the detector times the frequency of the source equals the frequency of the detector. If the velocity of the detector is positive, then c, which we always take as positive, added to that gives us a factor that's bigger than the c that we'd have in the denominator. Remember, velocity of the source for the moment is regarded as 0. Okay, so that case gives us a greater frequency at the detector than at the source. Now, if the detector is stationary and the source is approaching it, what does that do? Well, if the source is approaching the detector, then the waves produced by the source bunch up, so they're closer together. They're still moving with velocity c, but they're closer together. That means their frequency is going to be higher. So the source approaching the detector with the detector velocity 0 should give us a higher frequency at the detector. And that's the case because if the source is approaching the detector, then Vs is going to be negative, since the positive direction of Vs is this way. Vs being negative is going to make this denominator less than c. The detector is not moving for the moment, and the numerator is then c. So you have c over something that's somewhat less than c. Well, if you divide a number by a lesser number, you get a number greater than 1. So we're going to have a number greater than 1 multiplied by the frequency of the source, which will give us a frequency of the detector that's greater than the frequency of the source. So you need to understand that in the general image. Now, having understood that, it becomes very easy to solve a problem of this nature. So the problem on the practice test, the practice exam, says that the speed of sound is 347 meters per second, frequency of the detector is 330 hertz, velocity of the source is 0, velocity of the detector is 30 meters per second. And you can go with the sign conventions and verify that all these signs in this case are positive. So we want to know the force, the frequency detected by the listener. Now, see, I used L for listener. I knew there was another one of those lurking around there. That would be the listener is the detector. Okay? This becomes a very simple problem because we have 1, 2, 3, 4, 5 variables in the equation, and we know the value of 4 of them, so we can easily solve for the fifth. And it's even easier since the fifth is the left-hand side. We just have to plug the numbers in to the equation and we get our result. So I'm not going to go through the details of that. The main thing is to understand this equation, the sign conventions, how to identify your stuff. And this is just your basic, more or less mindless use of an equation. I do recommend that you understand the reasons behind the equation and how it's derived. But for the purpose of this test, you can get by just knowing the equation, at least for this problem. There are problems that ask you more specific questions about the behavior of the source, the detector, and so forth.